Alright, this is the Chapter 9 summary, and Chapter 9 is all about gas power. There are two things to note about a gas power cycle. The first thing is that the fluid is a gas throughout the entire process. It does not change phase, it remains a gas. And there are different types of gas powered cycles. Otto, Diesel, Stirling, Ericsson are just a few of them that we will be looking at in this chapter. All the cycles that we will be looking at will be idealized cycles, which means that we can analyze them more efficiently, and we can compare actual cycles to them. And as you can see, the dotted line here represents the actual cycle, while as the straight line represents the ideal cycle. And as you can tell, it'd be much easier to analyze the ideal cycle than it would be the actual cycle. Efficiency, not a new concept, same as it has been. The efficiency of a gas-powered cycle is the work net out divided by the heat requirement in. And something else that's the same, a Carnot cycle still has the greatest efficiency. And there are 4 stages of a Carnot cycle. The first stage is isothermal heat addition. The second is isentropic expansion. The third is isothermal heat rejection. And the fourth is isentropic expansion. So as you can see down here, I've drawn the processes on a PV diagram and a TS diagram. So from 1 to 2, isothermal heat addition. So we got Qin right here. And isothermal, that means the temperature doesn't change. So on the TS diagram, it'd be a straight line. From 2 to 3, we have isentropic expansion, which means entropy remains constant. So we have a vertical line on the TS diagram. We don't have any heat rejection or heat addition, but we do have some expansion going on. So we do have some work out. Just a little bit under the curve right here. It's a bad drawing, but you get the picture, hopefully. And then from 3 to 4, we have isothermal heat rejection. So isothermal again, we have constant temperature. And there is heat being rejected from the system. And then back from 4 to 1, we have isentropic expansion. So, oops, I made a mistake right there. I thought I was confusing myself. We have isentropic compression, not expansion. My bad. So, we would have some work in under the curve right here, but no heat addition or heat rejection. An important thing to remember in this, or to take from this chapter, is the air standard assumptions. If a problem says that a cycle is working under air standard assumptions, this is what it means. There are 4 assumptions, basically. The first one is that the working fluid is air and it behaves as an ideal gas. The second is that all processes are internally reversible. The third is that the combustion process is now a heat addition process. And the fourth is the exhaust process is now a heat rejection process, which returns the fluid to the initial state. Another important thing to remember from this chapter is relative pressures and specific volumes. This is handy because, as you know, on the on the property tables, air doesn't have a lot of the same properties listed as the superheater or as the refrigerant 134A and water. But what you can use is the relative pressure and relative specific volume, denoted here as PR and VR. But you can only use these ratios when entropy is constant. But this will help you figure out properties at any state in a cycle. If you're stuck, just remember these ratios, and you'll be good. Alright, let's talk about reciprocating engines. Excuse me. The compression ratio is an important thing to take out of this. It's denoted here as R, and it's just the ratio of the max volume divided by the minimum volume. And the mean effective pressure here, which is, sorry about that, which is what this MEP stands for. And that just equals the maximum volume minus, or the work net divided by the maximum volume minus the minimum volume. And some engine jargon that would be helpful to learn if you don't already know it, I have kind of written down here. TDC stands for top dead center, and that corresponds to the minimum volume. That's when the piston compresses, and that's as far up as it goes, top dead center. And then bottom dead center is how far the piston expands. And that's denoted here by BDC. And a stroke is basically the distance that the engine covers, or that the piston covers when going from bottom dead center to top dead center. And the bore is just the diameter of the piston. Alright, so there are two main types of cycles. One is a 4-stroke and the other is a 2-stroke. A 4-stroke engine just means that it completes one cycle in 4 strokes, which is 2 revolutions of the crankshaft. A 2-cycle it completes one cycle in 2 strokes, and that's 1 revolution of the crankshaft. So in a 4-stroke engine, the piston travels the length of the stroke 4 times. In a 2-stroke, it travels the length of the stroke twice. And the ideal cycle for a spark ignition cycle is the Otto cycle. And here I've drawn the PV diagram for an Otto cycle. It can be divided up into 4 processes. The process 1 to 2 is isentropic compression, and we have work in. The second, or the process 2 to 3 is a constant volume heat addition, and process 3 to 4 is isentropic expansion, and process 4 to 1 is a constant volume heat rejection. And here is the TS diagram for the Otto cycle. As you can see, we have isentropic compression here from 1 to 2, entropy is remaining constant, temperature is increasing, which means that we have compression going on. 2 to 3, we have Q in. 3 to 4, isentropic expansion, and 4 to 1, constant volume heat rejection. So we can solve an energy balance for the Otto cycle to determine the values of Q out and W in and W net and all that stuff for the cycle. So if we just look at 1 to 2 and we write out the energy balance, we have Q in minus Q out plus W in minus W out equals delta U, and of course you would have plus delta KE and delta PE, but for all this it's going to be 0, so I just didn't write them in. And if you take a look at the PV and TS diagram, you can see that there isn't any Q in, Q out, or work out, so all you're left with is work in equals delta U, and only if you have constant specific heats, or if the problem tells you that you can use constant specific heats, you can use this CV times T2 minus T1, or else you just have to use U2 minus U1. Either way would work, but just remember that probably would be a common mistake to make. And then process 2 to 3, we have the same energy equation, but as you can see, all that we're left with is Q in equals delta U, and so that'd be Q in equals CV times T3 minus T2. And then from process 3 to 4, same equation. We're left with negative W out equals delta U, which equals CV times T4 minus T3. And to get rid of that negative sign, you can rewrite it as CV times T3 minus T4. And then from process 4 to 1, same equation. Left with negative Q out equals delta U, which equals CV times T1 minus T4. So Q out equals CV times T4 minus T1. Just remember to keep track of your negative signs. Don't go messing up the temperatures. That'd be bad. Alright, now we're going to look at a diesel cycle, which is the ideal cycle for a compression ignition engine. So here I have the PV diagram for a diesel cycle. It can be divided up into two processes as well. Process 1 to 2 is isentropic compression. Process 2 to 3 is constant pressure heat addition. Process 3 to 4 is isentropic expansion. And process 4 to 1 is constant volume heat rejection. And you may realize it's almost exactly like the Otto cycle, but process 2 to 3 is replaced with constant pressure heat addition instead of constant volume heat addition. And from process 1 to 2 we have compression, so we do have some work in. From process 3 to 4 we have expansion, so we have some work out. And the area under the curve is the work net. Here's the TS diagram for a diesel cycle. 1 to 2 we have the isentropic compression. 2 to 3 we have constant pressure heat addition. 3 to 4 isentropic expansion, and 4 to 1 the constant volume heat rejection. And the area under this curve is Q net, which is also equal to W net. And here's the energy balance for a diesel cycle. Same process as for an Otto cycle, so I didn't write out the energy balance equations because we're pretty used to that by now. But from 1 to 2, all you have is work in, which will equal delta U, which equals CV times T2 minus T1. Oops, keep doing that. Only if the problem says constant specific heats or anything like that. Otherwise, you use U2 minus U1, and that goes for all of these: 2 to 3, 1 to 2, 3 to 4, and 4 to 1. Anyway, from 2 to 3 we have Qin minus workout, which equals delta U, and we can rearrange this to be Qin equals delta U plus workout, which we know is delta H, which I have written right here, and the definition of delta H is this: Cp, using Cp instead of Cv, times T3 minus T2. Yeah. Process 3 to 4, all we have is negative workout, and that's equal to delta U. So workout is equal to Cv times T3 minus T4, and I just rearranged those temperatures to get rid of the negative sign. And from process 4 to 1, we have negative Q out equals delta U. So Q out equals Cv times T4 minus T1, and I did the same thing that I did in process 3 to 4. Remember, these are the definitions of delta U and delta H. Delta U is always mCv delta T, and delta H is always mCp delta T. It doesn't matter if it's a constant pressure or constant volume process. If you have delta U or delta H, these are what you need to write in because it's just their definitions. So yeah, don't make that mistake because you'd be kicking yourself after that one. Alright, now we're going to look at a Stirling cycle. It can be divided up into 4 processes as well. Process 1 to 2, we have constant temperature, and heat is added from an external source. Process 2 to 3, we have a constant volume, and the internal heat is transferred from the fluid to the regenerator. Process 3 to 4, we have a constant temperature and heat rejection to external sink. And process 4 to 1, we have constant volume, and there's internal heat transfer from regenerator back to fluid. And I've drawn sort of a pretty simple diagram of what this is looking like. This isn't at any particular stage. This is just kind of the whole thing. We have a regenerator here, excuse me, which either cools or heats the fluid. And we have 2 pistons and a high temperature source and a low temperature source. And so, yep, that's a Stirling cycle. And an Ericsson cycle is exactly like a Stirling cycle, but the 2 constant volume processes are replaced by 2 constant pressure processes. And the efficiency for all these things are the same as the efficiency for a Carnot engine, which is 1 minus temperature low over temperature high. Alright, one last cycle that we're going to be looking at is a Brayton cycle. And the four processes for that are as follows. 1 to 2 is an isentropic compression process. 2 to 3 is constant pressure heat addition. 3 to 4 is isentropic expansion. And 4 to 1 is constant pressure heat rejection. And I forgot to mention, this is a Brayton cycle is the ideal cycle for a gas turbine engine. So here is the cycle diagram. We have heat engines here, or sorry, not heat engines. I knew I would make that mistake. I'll do this. Heat exchangers, and a compressor here, and a turbine here. And we have Q in being added from process 2 to 3, Q out from process 4 to 1, and process 2. Or I'll just reread the processes. So 1 to 2 is the isentropic compression through this compressor. 2 to 3 is constant pressure heat addition through the heat exchanger. 3 to 4 is isentropic expansion in a turbine, and 4 to 1 is constant pressure heat rejection back to state 1. So to sum it all up, we have the Otto cycle, which is the ideal cycle for a spark ignition engine. Diesel, ideal compression ignition. Brayton is the ideal gas turbine engine. And Stirling and Ericsson cycles, that they increase in efficiency by using regeneration. So that is it for Chapter 9, the gas power cycles. The end.